everyone. I welcome you all back to the post-lunch session of the last day of the Atal AICT Online FDP, organized by Mechanical Engineering Department, UCEOU. With great pleasure, I introduce Speaker of Session 15, Dr. P.V. Venkatakrishnan Sir, Distinguished Scientist and Director, CBPO ISRO Headquarters. And Sir will enlighten us with 3D printing for space applications, opportunities and challenges. Dr. P.V. Venkatakrishnan Sir is currently working as Director, CBPO, ISRO Headquarters, and has 37 years of experience in the domain of aerospace materials and manufacturing. Sir joined ISRO in the year 1983 in Mechanical and Materials entity at the Vikram Sarabhai Space Center, Trivandrum. Sir has made immense contributions in the field of rocket hardware and engine manufacturing, including cryogenic engines, material processing for metallic and non-metallic alloys like ceramic and glass ceramics, thermal barrier coatings, and high-end insulation materials. As a Deputy Project Director for Materials and Manufacturing in the GSLV MK3 project, Sir was instrumental in resolving the bottlenecks for getting the crucial hardware manufactured on time as per the requisite performance standards. Sir has won many awards. To name a few, ISRO Team Excellence Award as Team Leader for the years 2013-15, Dr. Biren Roy Trust Award from Aeronautical Society of India 2017, Distinguished Alumnus Award for the year 2017 from IIT Chennai, Lifetime Achievement Award from Rotary Club Chennai for 2018, Dr. S.B. Firke Endowment Award from ASM International for 2018, National Metallurgist Award 2019 from Ministry of Steel and Mines, Government of India. I welcome you, sir, and looking forward for your valuable presentation.
Sir, I'll just share, give the privilege, sir, as a presenter, just one.
Yeah, okay.
You are audible, sir. Clear picture is.
Okay. Am I audible to everybody?
Yeah, everyone, sir. It's audible.
Okay.
Yes. Now you can start presenting, sir. Share screen.
Yep. Is it visible to all?
Yeah, visible, sir. Visible, okay, sir.
Just go back. See, you are aware that, first of all, let me thank Osmania University and IICT and Dr. Sriramakrishnan and Sweta for the nice interface with the audience. And I've been just in and out watching what exactly is happening for the last 1 week here. And I have been seeing a lot of presentation on and off, listening to it, giving you the details of how to 3D print, what are the requisites, what are the intricacies in this, what is the kind of expertise available in the country or elsewhere in the country where we need to leapfrog. All these things were discussed. I was just watching it. In this presentation, I won't be talking much about 3D printing technology because already I think 1 week you have been listening to that and you are well aware of exactly what is 3D printing technology. I would like to just share exactly what is the challenge in space components and space systems to migrate to 3D printing. What are the challenges we are facing? And there is a lot of scope for research in this particular area of migrating to 3D printing in the coming years. I will tell exactly why we have not been doing it so far. What are the bottlenecks? What more need to be done in this particular arena, and how we can migrate to 3D printing. The possible areas. I won't say that all areas are possible. To that extent, I will just make it clear in my presentation. And the rest of the things, I think we can discuss while going through. I have some slides. I think it will be self-explanatory. I'll be just going the way in which how the other countries are doing it right now, and where are we right now, this particular aspect. The current manufacturing methods, what this 3D printing will be replacing, when we are possibly migrating in the coming years, will be electrode discharge machining. We are doing certain components that also we can do away with if you are going for 3D printing. Investment costing, that is lost wax process. You are all aware, I think, lost wax process, the wax model. This one is melt, and the entire thing is being again replaced by your metal, modern metal, and you will get a somewhat good shape. So intricate castings. Normally, it is done for ornaments and all, for small ornaments, but due to the intricacy involved in cryogenic engine parts, and a lot of investment castings are being used with the interface machining alone. The interface alone will be machined for joining it or bolting it or making it integral with the next subsystem. And CNC machining from forged blocks. So you must be aware that from forged blocks, if you CNC machine or if you EDM, a lot of wastage will be there. And all the alloys, what we are doing, what we are using it in our space components, space launch vehicle components and spacecraft components are very costly alloys. All of them were imported some time back. And right now, almost 99% of all of them are indigenized in various forms like forged blocks, extrusions, forged rings and ring rolled rings and everything. And sheets, of course. Aluminum alloy sheets, if you go through all aluminum alloy sheets from 2219, that is copper alloy, 3 silicon, 4 magnesium, 5 magnesium silicon, 6 is again manganese, magnesium silicon, like that, everything. 7 is zinc, 7 series is zinc. All these things are actually in various product forms like extrusions. 775T, 7351 condition extrusions are being made by Ambajari, and the alloy is made in Hindalco Hirakud, and the 2219 forgings, ring rolled forgings are made in Chengalpet by Bayforge, and you have that castings coming from the cast house in Balco, Korba. So all these things are integratedly done in India. A lot of money and a lot of effort has been already spent on this process. And to see that if you want to just migrate for fun's sake to 3D printing and you are ending up with more costly and more time taking, it's not that easy. So what we need done is selectively we have to migrate to 3D printing, and next generation launch vehicles you have to design for 3D printing. Then it may be economically viable, and small volume production, that is another thing. I'll come through all these whatever small bottlenecks what we are exactly facing. So well understood practices and procedures we are following right now. Very difficult to, change management is very difficult. Changing from anything what is ongoing for comfortably. Any comfort zone changing is very difficult. And change management itself is a topic where we all discuss about how to migrate from this to that. And component technology, the actual propulsion system and all, if it is changing, it is inevitable. But the process change for production is a desirable thing. So the EDM produced component as well as the 3D printer component, both are giving the same efficiency, same performance. Means the questions will be raised. What is the advantage of going for 3D printing then? Unless it gives me an additional performance. We all talk in terms of performance. So unless it gives additional performance, no additional performance, because configuration remains the same. Only the process. Then the only thing what we are looking for is there is time saving and there is cost saving. If these two things are not there, we will not be able to migrate into 3D printing. That is the main thing actually. There was a 3D printing summit. There is a 3D printing workshop what we conducted, one full day for the entire space components and all, with all 3D printing experts like GE, Wipro, everybody participating. And we had a brainstorming session. I'll come through that. Exactly what is the outcome of that also I'll tell you. And these are the challenges what exactly we are facing. And that is the challenges for all of you people who are attending this workshop here, to go through and go back and work on that and come back with solutions for all of us. So if you are able to provide us, at the end of the day, you are taking away this message. And if you are able to come back with viable solutions for us, what we are posing here, and that I think that will be great advantage for us. And that is the one which we are looking for. That is the advantage I'm looking for here when I interact with you. Major alloys, ferrous as well as non-ferrous are indigenized already. And atomic, if you want to make a powder form for all these things, it is going to be again all the powders, all exotic alloys, we have to make powders now. All are again going to be imported. Right now, only one indigenous phase is over for all of us. So again, if we want to restart the cycle again, and you want to depend upon when the Atmanirbhar Bharat is going on, if you really want to again change the table, and if you want to make it depend upon other countries again once more, that will be again one question mark posed. So operational supply chains are established already. "3D printing as alternative, when we can go cost effective without major redesign in existing well-proven space system if it is cost effective. But at the end of the one full day 3D printing workshop, none of them promised me. I have given the purchase orders and what is the end-to-end product, what is the forge block cost, what is the machining cost, what is the surface treatment cost, what is heat treatment cost, everything I got, the some sigma of that I have given to them. The end of the day, the total cumulative cost of one component, if you want to replace by 3D printing with imported powder from outside, all put together. If I want 15 numbers, my launches are only 15 per year or 15 PSLV per year. All of them are none of the components are repeating in space systems. You must be knowing all of them are unique. Only rivets and fasteners and joining things are repeating. Otherwise, all of them are unique components. If the 15 components per year to be made by this through this particular route method, replacing the existing cost-effective method, you must give me a cost advantage or a schedule advantage. If both are not there, it doesn't become attractive or lucrative for me. So that they were not able to give me. They very clearly told that is going to be more costly, sir. One thing I want to tell here, all the 3D printing enthusiasts, but you can go for small toys, small bangles, or whatever you are producing, a small pen or something from 3D printing, a small bracket. But space systems, you really want to replace with 3D printing, we need to answer these questions when it goes for any kind of a modification in this existing system. Feasibility of low volume production with considerable cost as well. There is a fallout of the first thing what I put right now. Ensure alloy uniformity in powder form. There is one more challenge. Alloy segregation may take place because the kind of alloys what we are having. One example: copper, zirconium, titanium, and chromium. CuCr, TiCr, chromium is one typical alloy used in inner divergent chamber of cryogenic engine. You must see that chromium, copper, the highly dense titanium is right. There will be segregation. I want powder homogeneity. Alloy powder once made, after that I want homogeneity in powder actually. And that too, if I use it in space systems and all, there will be deoxidation, there will be radiant heating, everything. The vaporization should not happen. All these things put together, the integrity of the component, whatever you have made, should be as integral as what we are making through forging system. Final product homogeneity, that's what I told some time back, the final homogeneity, withstand rigorous testing and qualification procedure. See, for me, any qualification, whatever you do, like pulling or putting in UTM or anything, is not sufficient for all of us. So like long transverse direction, cross transverse direction, or longitudinal direction, tensile testing, then yield strength, then modulus of rigidity or elasticity, all these things are not sufficient for me. That is one part of it. Apart from that, the entire component and engine has to be put together and integrated. There's a leak check. Finally, it has to undergo one hot test. One hot test is nothing but firing of the engine in the ground in the test stand. Once it is undergoing the test only, I can say that the component is qualified. So for one component alone, I cannot go for I cannot go for a hot test, because one hot test is 1 crore, almost 1 crore for me, including propellant, everything put to the effort, the test stand interface, all is put together is 1 crore for me. So if I need to qualify one component made out of 3D printing, substituting the component made out of any other process, and I want to test it, it is going to be extremely costly for me. So what I can do is I have to go for 3D printed engine totally. Then go for one test. But I am telling you that is going to be very costly engine, because many of the components, if you go for 3D printing, is going to be more costlier than the existing methods. So there is the kind of a trade-off required then. What is the kind of trade-off required? To produce certain components which is economically viable and replace it, and certain components will be manufactured with the existing whatever way we are producing right now, both we can combine together in a hybrid form, then test it. So that need to be done, and that to be a schedule. The schedule wise, it should be less time taking for me, as well as the cost also should be less. Then only I can migrate to 3D printing. Hope it is clear to you.
Clear, sir.
Yeah. 1 minute. Yeah. So there was a 3D printing summit. What kind of approach what we have made is 3D printing summit 2018 in collaboration with the Additive Manufacturing Society of India, AMSI, platform to bridge the gap between required end users, ISRO centers, and solution providers. 3D printing industries both were meeting together, and they have shared the platform, and we have exchanged our ideas. Participation from all major centers. So whatever it's coming out here has discussed that time also. It is coming to a different audience now. Okay, the presentation from select industries also were made. Salient points being presented next. It's coming now. Engine components and subsystems. You can see this complex engine. This is a semi-cryo engine, or LOX methane engine as we call it actually. It's a natural gas methane engine. This is going to be designed now. What is going to be designed? We thought we'll design for additive manufacturing. Also, I am saying it is additive manufacturing also, not additive manufacturing alone. Because if at the end of the day, if you are proving that the existing methodology of a manufacturing or process of manufacturing is going to be again cheaper than 3D printing, we'll again stick back to our process only. We will not be able to go into 3D printing. But we have combined some components to make it, the joints are less and 3D printable, more amenable for 3D printing. That way we are manufacturing to see that easy migration to 3D printing is possible. And the quotation, we are going to get the same components for the existing methods also. We will see how both look like, and if then only we'll be able to take a decision, a call on the day, at the end of the day, finally, whether we want to go for 3D printing or not. But the exercise is on. Unless you do this exercise, I can't give a concrete answer for whether I want to go for this, because two things are there. One is 3D printing is whatever you said and done, if whether ISRO is using, or whether the country is using, or whether you are using or we are using, the world is moving towards 3D printing. So at some time, the entire components will be manufactured through 3D printing only. There may be a kind of, this is going to be disruptive technology in the years to come, definitely, I'm telling you. Even now also, die casting industries, all are really in trouble actually. They have been forging industries, small forging industries, die casting industries, all are having their own fear about this 3D printing going to be a real threat for all of them. So the years to come, when all others are doing by 3D printing, and other machines may not be available in the market also. Because you must understand one thing, almost all of the manufacturing machines right now, what is available in India, whether it's complex or even simple, except for simple lathes and slant bed lathes and knee milling machines or drilling machines, all of them, after the, even HMT has perished long back, and there are some companies which are making other small machine tools and all. All other larger machine tools like stretch forming machine or anything, whatever you talk about right now, is being imported. So even the existing machines may not get maintenance and all of things out in the years to come, because 3D printing sometimes may take over the entire scenario, and everybody will migrate to 3D printing machine making. In that scenario, the existing machines, whatever you are right now having in country, may not get the backup support for maintenance also. So you must understand all these kind of geopolitical situation, kind of what is the future dynamics, what is going to happen. Apart from technology, techno-managerial views also has to be seen before taking a decision. So unless we are familiar with 3D printing and making us comfortable to migrate to 3D printing at any point of time, even at a slightly higher cost, we will be losing in time. So we want to equip ourselves to see that at any cost, 3D printing, if you really want to migrate, there's no other go. At some point of time, 3D printing is going to be the technology of future. Definitely at that point of time, we should be able to migrate to that. So at that level, we should be able to equip ourselves and technologically make us sound, so that we can do it at any point of time. But we need not take a call right now, because it is going to be expensive and not going to be economical at this point of time. This is the kind of policy or whatever guideline we are following right now at this for 3D printing migrating. This is semi-cryogenic engine status hardware realization is going on. This is a methane engine is under design. So methane engine, this we are not able to do anything right now because already the design is over and 3D printing is not. We are looking into that. But LOX methane engine in the future engine are exactly the turbine blades, the kind of outer gauges and all these things, inner pipe, all these things. We are trying to make it more amenable for 3D printing. Whatever, for at least 400 mm into 400 mm machines. Once you get that, not to that size, the machine also may be 400 mm to 400 mm. To that extent size only we are trying to limit it so that now we more maximum 3D printing we can do. So some exercise we are doing in-house right now to see whether it is the 3D printing technology. That cost we are not comparing now because developmental cost we are not comparing because that is the technology development cost. That will be always kept aloof for ISRO because otherwise now you won't be getting technology. After that, the production cost comes only once you make the prototype and proof of concept. This is a roadmap actually right now. Liquid Propulsion System Center is one center in Trivandrum, which is making the engine components and all. Most of the structures and structural components in rocket motor case are made in VSS Vikram Sarabhai Space Center, whereas the engines and engine components and the control component systems were more amenable for 3D printing. Very intricate parts, intricate internals are involved. All these things, CNC machining, or even investment casting, all this. So what there only we really want to migrate to 3D printing maximum. So I am taking example of Liquid Propulsion System Center in Valiamala, which is the prime center for liquid propulsion technology for us. So you can see that parts amenable for 3D printing, 50 are identified right now. That is the exercise what we have done right now. Inducer can be done in 11 hours, stator can be done in 12 hours, rotor can be done in 30 hours, exhaust casting can be done in 70 hours, propellant tank, of course, which we are not worked out actually. It is a reason, it's a different methodology we are doing. Is additive manufacturing process for LPSC, direct metal laser sintering for parts up to 400 mm cube, electron beam additive manufacturing for gas bottles and tanks. These are the two technologies what we are looking for. Achieving complex shapes, weight reduction. What are the AM benefits what we are looking for in ISRO is achieving complex shapes very easily, time saving also, and weight reduction by comparing the parts, monolithic construction without welding. So that gives you more reliability because joints are not there, means more reliability, and our reliability factor of the engine or the rocket also will go up like anything. Faster production and permits design iteration. So that also another thing actually, faster design and faster design realization. These are the things which we are looking for in 3D printing. And design for AM adoption and LPSC, what is going for design for AM, especially for the next generation engines and all, sample validation, part validation, production. So the kind of timeline what we are looking for is rate contract for building the parts, rate contract for, you can see the timeline given on top. By 2022, we are trying to have 25% replacement of all complex parts with AM parts by 2022. It's 2020 and what is 19 here is wrong actually, 2022. So this 25% also we are aiming. I can only say we are aiming. If it is not viable, it may not be 25%, maybe 22%, 21%, 20%, 19%, 10%. So if it is not economical, we are not going to do it. That is another thing what we want to really do. Drivers of 3D printing in NASA. You can see that NASA has 3D printed, tested thrust chamber. Thrust chamber is nothing but convergent divergent chamber in the lower end of the part where liquid engine thrust is being produced. It's a nozzle actually. It's convergent divergent nozzle. Stage car propulsion project. Final test went on. See, you must understand one thing. One important thing that migrating 3D printing in Rolls-Royce engine parts, component parts, or any kind of NASA or ESA parts right now we are seeing, the effort has started around some 8 to 7 years back. So it's not an overnight changing over to 3D printing. 7 or 8 years back they started the efforts, but we are going to start right now only. So hence, but we will be saving some time because we have the knowledge of these people already done and what is the kind of literature survey, everything. So we have some more knowledge. It may not take 7 years for us. It may take 3 or 4 years for us from right now to start from right now. So that is the one advantage we are going to get. But already others have migrated. We are still to migrate. And 3D printing is, as I told some time back, is going to be the technology. Means we have no other go. We have to migrate sometime out at some point of time. At least not now. At least later. It's aim to reduce time of cost involved in building rocket engines parts through additive manufacturing. That is the idea. That is the aim. For NASA, actually, copper combustion chamber. Inner chamber of the divergent of the cryogenic engine is, as I told some time back, is a very crucial alloy called, which was imported from Russia. We are indigenized through NFTDC Hyderabad right now. NFTDC, Non-Ferrous Technology Development Corporation, is doing for ISRO the entire thing. We have just made 15-16 crores investment there, and they are doing it for us now. For a 1/4 the cost of import. You must understand 1/4 the cost of import. A product slightly superior than what we are importing. So you must understand the kind of the kind of expertise available in the country if you are really able to focus on that. This is a copper, chromium, zirconium, titanium alloy, tertiary alloy, which has got a high diffusivity, thermal diffusivity. That's why it is being used, because it should not get heated up and melt. It's the inner chamber. It's 525 channels on the convergent helical channels are the milled. That milling alone, actually, if it's a monolithic product, all welder construction, if somewhere something goes wrong, the entire product get rejected, even in milling or in welding or brazing. And we got 7 brazing alloys in that with different melting temperatures. You must understand. So each one is brazed in each different stage. The last one, if it is brazing, the first one should not melt. So the brazing alloy temperature should be less than that they already brazed joint. So brazed alloys are to be developed in melting temperature in lesser than the previous brazed part. So you must understand that is another constraint what we are having, to have a kind of brazed foil or a brazed alloy to have a different temperature which is lesser than the previously joint brazed component, because the entire component again go into the rotary vacuum brazing furnace. Is RVBF, rotary vacuum brazing furnace, is another one which we have imported from Russia. Right now it is being done in India by Hindustan Hi-Vac. It is around 18 crores. It's unique product, a single point product. Actually, this is a single point failure product. If something goes to that wrong with that for that particular equipment, you cannot make the engine again. So it has to be maintained properly. It's you have to have heavy maintenance cost for that, alloy cost for that, 50 microns and 5 microns for the alloy. We are making an NML Jamshedpur actually. So the entire country is contributing to the process of even for making one small cryogenic engine. So the technology is already on. If you want to go for 3D printing, there won't be brazing, there won't be RVBF. A lot of things can be. It's going to be a highly disruptive technology. A lot of technology will be replaced on single point technology. You can have 3D printed with internal copper alloy, with external is SS301. SS321. So outer chamber is SS321. Both you can have a 3D printing technology, 3D printing concurrently being done the same machine. You really have a single machine for all these things, and time is going to be, and 0.5 mm is the outside SS321 thickness. To get that, it will be of my height, around 6 feet height, the divergent. To get such a kind of thing like zeroed foil and making it stand alone is going to be extremely difficult for us to form it and keep it. And you have to put on the inner chamber cover, the channel outside. Then in between you will be having that your base foil, and you have to have the rotary vacuum furnace, and you have to braze it. And it should be leak proof and leak tight. Each channel should not communicate with each other after brazing. And there is a kind of there is a radiography testing, there is a water channel testing, water content testing for each channel. Through each channel, if you pass water, it should come through the corresponding channel outside, that it should not come through any other channel. So these painstaking tests are being done individually for each engine before flying, before going for hot test. And each engine goes for hot test before flying, because the hot test is the only one which we are making sure that the entire thing finally works together. One hot test is 1 crore. So these are the kind of things. And in 3D printing, if you want to migrate, all these things have to be repeated for qualification. That is going to be very costly for us. So unless we prove that it's going to be economically so viable, our board is not going to really permit us to go for this particular thing just for the sake of technology change alone. So that is one important thing what we are going to highlight here. So copper combustion chamber liner was made out of selective laser melting for NASA. Combustion chamber jacket of nickel alloy. Nickel alloy is a super alloy, actually was produced from electron beam manufacturing and that is Inconel 625. and GrCO84 copper alloy. They have got different copper alloy for this particular thing, and we have got different copper alloy. The LPSC scenario compared to this is development of composite thrust chamber for 20-ton LOX with an engine that will be semi-cryo engine as well as the next generation. This eco-friendly LOX methane engine is going to be eco-friendly. It won't contaminate your the unburned or unused fuel is not going to contaminate the sea or anything, even the atmosphere. The double wall construction with internal copper, whatever we have developed right now, and outer chamber is 321 steel. 300 helical channels are going to be milled. Advantage 3D printing is avoid milling in helical channels. You can print it, you don't have to mill it. It will be more uniform. Avoid brazing. Brazing is not required. The rotary vacuum brazing furnace is not required. And reduction in number of parts also. We can integrate number of parts because there's no outer chamber, there's no inner chamber. If you can put it together, it can become a single chamber actually with a sandwich construction. Okay. The configuration, I think you have to see it in mind if you really want to follow my lecture. Actually, I think it's a nozzle, convergent divergent nozzle with inner outer chamber. Inner chamber made of copper, outer chamber. Both are being put together and based, and the combustion products are regeneratively cooled by passing it through through these channels. When the combustion products are coming out, the next hydrogen is getting heated up through regeneratively passing through through the walls of this chamber, so that it becomes preheated. So highest efficiently we are using even the products of combustion, we are using it efficiently for next preheating the next fuel. Okay. The conventional production, 800 close holes are to be drilled. So in LPSC scenario, 3D printing and Ariane 3D printing, I've just come to that part they are doing right now. In Europe, we have been talking about NASA right now, and the equivalent one in LPSC Trivandrum, what we are doing. The same thing what we are talking about, if you talk about ESA scenario, European Space Agency in Ariane, conventional production, 8,000 close holes to be drilled in copper sleeves, precisely screwed to 122 injector elements. You see, the injector elements are screwed to 122 elements here. See, it's called injector head. It comes in throughout of the combustion chamber, and that is it is going through this thing only. Actually, the products of combustion are being just burnt, atomized and burnt. Okay. 3D printing 120 injection nozzles, base and front plates. So the entire thing is after making individually as they're screwing, that is going to be a monolithic component 3D printed right now in Ariane engine. So we have been following it exactly what they're doing. Components cut from 248 to 1. You must understand 248 to 1. So 248 components, space has got different way of doing things. There's a traceability. You need to have the history card available for each component. Each has to be traced separate. Each has got inspection report, snacks report, and there is a non-conformance board actually available for each of the non-conformance. The board has to meet the minutes has to maintain everything. So 248 components mean 248 reports will be there. You must understand the report making and documentation also is equally important in space, and that is a very, very cumbersome affair. And so that way, if you see, 248 is just you need to have only one report. So there is a tangible and intangible benefits when your number of production parts are going to have. Your archival history, your volume of archiving, everything will come down like anything. Your history tracing, everything will be easier. Conventional production, casting and machining, 3 months. 3D printing, 4 lasers, time taken will be very less. We don't know how much it is. Ariane has not really put that, but must be less. Otherwise, they won't go for that. Okay. The LPSC scenario we are having, you must see this. These are all injector heads. All are injector heads. And it is made by EDM process, electrode discharge machining process. It is made of SS. And this is an SS manifold and outside manifold internally. And you have braze foils in between this annular space. You have braze foils here, and the entire thing goes for brazing together. Each one of these injector head is water calibrated, and the efficiency is measured. After that, the designer, it goes back to designer. Each one of that has to be again, he will reassign this component, actually one component again in the circle, again inside. He will reassign numbers actually to get maximum efficiency. So each 169, it's only a typical one I have shown here. 169 elements are there actually. One of them is having 530 elements. These 169 you see, you cannot put the 169 again back. If all of them are alike only, you can put anywhere. It is totally interchangeable. If it is having a different value in water calibration, each one of these injector head has to go for water calibration, just to come back after water calibration. After that, designer is again a typical unique position for each head after the water calibration numbers are made available to him. So it has to go to a unique position here, then only you can trace it. You must know it's a very laborious process. If you make a manual mistake of putting it somewhere else, the efficiency will be less actually. So that is because you are not able to make it alike. If you are able to make it alike, if you are able to make it uniform, if you are going to get uniform output number for the water calibration, this 169 will become totally interchangeable anywhere you can make it. Because it is made of single components only. If you make it an integral component, the component again reassigning and all these efforts are. I am trying to explain to you how it is being done right now. The laborious process of again reassigning the number, everything will come down like anything because it is very monolithic. But only thing is, even in this monolithic, the entire 169 should behave uniformly. Each one should not differently behave from the next neighbor or any other injector head. Just uniform. It will be uniform because you are going through a automated process. The entire process of your powder deposition is going to be automated if you go for 3D printing. So that is one advantage you are going to get if you really migrate this particular component to 3D printing. At Ariane, what we are doing actually, Cosmos next generation rocket engine launches in 2030. Again, you can see that you 10 times less than the current rocket engine on Vulcan 2. GKN Aerospace Sweden will be developing the manufacturing full-scale turbine. They are also going for turbine, all turbine parts from more than 100 to 2. The 3D printing will reduce the number from more than 100 to 2 numbers. Actually, all the turbine parts, everything put together in the Cosmos engine. They are going to next generation engine, like what we are making our methane engine next generation. The LPSC scenario actually locks methane engine. I'm just comparing here what we are doing right now in the same platform. Design for additive manufacturing we are right now doing and comparing the parts, actually breaking down the parts, and it's going to be more cost effective to design for 3D printing. The existing engines we are not able to migrate only because not designed for 3D printing. Rutherford engine, liquid propulsion rocket engine designed for New Zealand by Rocket Lab, is manufactured for United States. You can see that fabricated by 3D printing, electron beam melting. This is made by electron beam melting actually. Another slide on Rutherford engine, combustion chamber. Time taken we are not knowing, but there is a considerable time advantage for this we are told. So same thing we are following here also. The engine can be made in 3D print in 3 days. You must understand, an engine of this complexity, if it can be made in 3 days, nothing like that actually. See, the future is going to be like Ola or Uber. Actually, you must understand. We are going to make one SSLV. You are hearing from newspapers and all, small satellite launch vehicles. There is a small satellite launch vehicles up to 500 kg. We are going to launch through that particular because even now for 500 kg or 400 kg we are using PSLV, which is going to be waste for all of us because PSLV right now can carry, even though it started from 800 kg. Now we have optimized to 1,800 kg. A 1,800 kg rocket, if you really want to use it for 800, 400 kg or 500 kg, it's going to be a lot of loss of. If propellant you will not be loading much, but the entire hardware, everything unnecessarily, inert mass, weight, everything is a loss actually. You can optimize it a little more if you want to really carry 500 kg only. So we are going for a different class of vehicle called SSLV right now. SSLV can be launched in 3 days. The checkout systems are through a laptop, the interface and all these things are go through a laptop actually. And your launch campaign only will be 3 days. If you order today, I want to launch day after tomorrow, we can launch it. That is it's almost like a Uber or Ola taxi stand. We are just asking for a launch. You are just obliging that. So if you really want to get into that kind of a system, 3D printing is going to be really effective because if you want to make it, more number of orders are going to come for launch from outside countries also. We need to produce it faster rate. So this is going to be 3D printing is going to be really advantageous if you really migrate to all this new future generation low cycle time production rocket, small rockets. If you really want to migrate, 3D printing is an app technology. Here also, you can see electric pump of locksmith and engine will be generated incorporating design of additive manufacturing rules. So these components, number of components you can just see here, is going to be integrated to one actually. And different alloys are going to come here. Each color is a different alloy. This alloy, whatever we have shown, blue and blue are actually same alloy. I'm just explaining to you because these alloys can be made through 3D printing to integral one. Exactly through 3D printing, migrating from one alloy to another alloy. You need not go for a different component production here. And Lockheed Martin, what they are doing actually for 3D printing is, you can see that it's a titanium test tank. They made it 2 3D printed domes, service caps, and variable traditionally manufactured titanium cylinder domes the country. So here entire thing is made by 3D printing actually. Here also a lot of cost advantage and time advantage is there. Here LPS scenario, you have propellant tanks in satellite as well as in rocket engines. Both have got a cylindrical in the middle and the end got domes like this, like a hemispherical shell. This hemispherical shell is to be made through a wire is being wound actually, wire is being wound. A thin wire of what titanium is being wound to this shape and is fused and melted actually through electron beam welding additive manufacturing. This is one technology what they have demonstrated here. And this is one we are trying to make a titanium satellite tank domes in LPSC Bangalore here. You can see 3D printing. The pathway of progress to LPSC is whatever the one center what we are mainly making 3D printing efforts actually. Additive manufacturing journey, you can see adoption, technology presentation, AM workshops, printing. We have got an elaborate process of migrating actually. We can't just like that do. We make a very, very economic economic analysis actually. It's a technically also how we are strong. So another area where we really missed actually something is, one fourth block. If you really want to qualify, you have to take one small strip of your test coupon, UTM test coupon, in longitudinal direction, in transverse direction, and in long transverse direction, and pull it and see. And you need to have the kind of your hardness test and everything. And once it is qualified, any component making out of that, you make 500 component out of that. This one test coupon will do for the entire 500 components. But independently in 3D printing, if you make 500 components, how to qualify like that? Just one forged block qualification is qualifying my 500 products made out of that in the existing system, or what kind of practice what we are following. But right now, if you make each component separately, what kind of qualification? Unless you process the qualify the process like anything, there's not be any process variables, everything. So that is going to be a real challenge actually, migrating from product qualification to process qualification. Here, more we are depending upon the process uniformity and process qualification than the product qualification. So that is a philosophical change for ISRO. That is one thing which I want to highlight here. So selective laser machining, our direct laser sintering process, parts up to 400 meter cube, we are going for that. And electron beam additive manufacturing for gas supporting propellant tank. These are the two technologies we have just decided to go ahead with whatever minimum possible with 25%, as I told sometime back in 2022, 25% product will be replaced by 3D printing if it is economically viable. And typical parts and 3D printing time, you can just see that building time is 30 hours for your rotor. This made out of EDM now, electron discharge machining. It's a kind of it goes for around almost 1.5 months in one EDM machine. So now it will be done in 30 hours. But we don't want at this stage. Actually, we want only 12 numbers per year. That is another challenge. If you want 1,000 numbers to be made in no time, I think 30 hours is going to be really painful. The question asked to me when I go with this presentation or proposal tomorrow is that, why do you want this fast? I don't want this much fast. So that is another challenge I'm having. I want only one in a month. So existing technology is enough for me, unless we get into more number of launches in the years to come. So we have to project a kind of scenario where we are going to really make more numbers in the future, futuristic. That is one thing. Second thing is, as I told some time back, if 3D printing is going to be the technology and all other technology is going to be wiped out, we should not be lagging behind in not having the technology. For that, we should be having the technology. At least some parts we have to continuously produce through 3D printing to stay alive in 3D printing area the years to come. So that at right point of time, if no other technology is available, if we are forced to migrate to this technology, we should not be losing time, and we should be able to migrate to this technology. So that is two policies we are following actually. This is really going to be disruptive because the way in which the world is moving towards 3D printing technology is enormous speed. So we cannot keep idle. We have to see whether it is not, whether required or not, we need to jump into the sea and we have to see that something is being done in this area also. So understanding that particular scenario only, we are trying to see that what is the minimum thing what we can really get into. And understand the philosophy of making it 3D printed technology for other components also and keep ready for any kind of migration in future if it is compulsive. Inducer is another one which is going. No, you just see it's a CNC machining which normally go in MTR Hyderabad actually for almost a month in one 2D machining. It's a typical special purpose machine which we are imported from Russia. It's a disc cutter actually. It's not a ball cutter. It's a disc cutter. Two disc. You can see disc only you can cut here. Then only you can get this kind of a envelope. So these are all easily made by 3D printing in 11 hours. But what is the advantage I'm going to project in 11 hours? If in 11 hours, if I want to produce 12 parts, I will produce in 2 days and keep it idle. I'm going to use it in the 12th month only. That is another challenge for me. So you must understand migrating is not that easy and we have to prove economically viable. And if it is going to be so cheap only, I can advocate for this. Otherwise, people will say that if it is going to be costly, time alone is not going to really answer all the questions asked by my parties if I present the in my review forums. The inlet branch time is for 140 hours here. Actually, you can see Spider is another 220 hours. This already I've seen. This exhaust casting is done by investment casting as well as interface machining. Now it will be done in 70 hours. 70 hours now. Okay, build up time. So this is a stator. This is got an outer casing also. Without outer casing, I've shown some time back like this. The outer casing also. This yearly you want to EDM if you want to do, you have to make it ulta and do through another cathode from the other side actually, copper cathode. So 2 copper cathodes are required, one from this side. You can't make it through. So you have to make it again, align it to the next. If you want to make it ulta, again you have to align it properly. That is another technology actually. But we have mastered it right now and we are doing it. But in 3D printing, you can do it without any problem of kind of aligning of through cathode from both sides and all these things. If it is open like this, you can approach from the side and do it faster. If it's closed like this, you have to approach from both sides. That is another thing which you right now face. But we have mastered the technology. Okay. Flow straightener, impeller. These are the things out of 50 what we identified typical products which we are really trying to migrate into 3D printing. The structural parts right now, like thrust frame support and thrust frame, whatever, these are all typical thrust frame supports. These are all structural components. Easily we can migrate because functional parts, there's no flow, there's no pressure vessel, there's no rotation, there's no RPM coming here. So these are static parts which we can easily migrate. You can see these are either these are typical investment casting. You see, second stage volute body is a cryogenic engine. ICSS means Indian cryogenic stage steel. 14, 18, 200. These are all made in Midhani, actually, Hyderabad. This is investment casting with interface around machined. These are, you see, this interior actually is very highly intricate pockets are there internally. So all these things are easily amenable for 3D printing. You can see that here. Obstructing my view, actually. That's what. Okay. These are all typical structural elements actually for easily made for 3D printing. This is already we have 3D printing. It doesn't make money any kind of a. These are all sheet metal products flared and made actually and welded. So easily we are going for 3D printing right now. But engine component 3D printing will take more time, as I told some time back. C20 brackets for 3D printing. CUS, this is cryogenic upper stage. It's called CUS cryogenic upper stage brackets. for 3D printing. Semi-Micro engine 3D parts printing, typically what we are going for 3D printing. These are all typical parts easily made for 3D printing. Satellite thrusters, you can see satellite thrusters. Not all the, say, new powder development is required for niobium. C108, columbium. Right now we are making through NFC Hyderabad. We got a columbium plant, the niobium columbium plant. Just now introduced, indigenized 2 years back. And if you see 108, if you really want to make a new powder development, it's going to take me another 10 years. Say, 1,800 degrees centigrade this has withstand, and it's a highly thermal resistant material. Thermal barrier coating is not required inside this. It's called columbium and niobium. And this, if you really want to make powder for this alloy and you don't want to import, it is going to take another 10 years from now. So this technology sometimes, because if it is all exotic alloys, it's taking me back by 10 years. You must understand. Sometimes no, it's taking me back by 10 years more. If you're really talking about Atmanirbhar Bharat, self-reliant. If you're importing, of course, no. But we have been importing for quite a long time. Atmanirbhar and self-reliance, actually, ISRO has started long back before all these words were coined right now. 10, 15 years back, we have been working for self-reliance without anybody's encouragement or anything. It's now been a policy, because this high-end technology at any point of time, people may say tomorrow I won't give it. So it should not be standstill, and your technology should not be taken to a ride. So you should be able to launch your satellites and rockets then also. So you must be Atmanirbhar or self-reliant, even at a higher cost. That is the policy ISRO has been following in the years, the past so many years. Manifold assembly, this is another 3D pilot project already we have done through Wipro. Semi-Micro, many Inconus 718, it's a highly hard alloy, super alloy actually. This also we have made a pilot ongoing project. Then this is electron beam belting. I sometimes with wire also wound actually, and you are fusing it through electron beam source. This also we are now trying to make one product through this method, especially this dome, which is right now made by plate route. The alloy comes from KMML, titanium sponge comes from Kerala Minerals and Metals from beach sand. Titanium dioxide, they are reducing it to beach sand to titanium sponge. Titanium sponge goes to Midani and they make it to A6L4V. They make the alloy actually. After that goes to Visakhapatnam for your BHPV. Earlier BHPV, now BHEL has taken over. The plate is given there actually. The plate is made into, by dome processing to a kind of a semi dome actually. The dome comes to again Trivandrum for BrahMos for machining it for dome machining. Then the entire thing goes to BHEL Ranipet for making the tank. And for electron building, it comes to again Bangalore LPSC. Then pressure testing goes to Trivandrum and Mahendragiri. So this is the way a tank is being made right now. The entire South India, almost South India, from Visakhapatnam to Bombay to, or if it is not plate route, if it is for forge route, it goes to Bharat Forge Pune. So entire southern India actually below the Vindhyan is involved in making a small tank just to see. So if it is a 3D printed machining, it can be made in under one roof totally. There's no different process can be eliminated and the common process can be evolved, provided it should have integrity. It should withstand the PPT, the proof pressure test once it alloy integrity. Titanium and zirconium, if you put together, the alloy segregation because of density difference should not happen in powder and all. Because if you make micro powders, sometimes if you take a small micro powder, it will not represent the alloy. It may be sometimes the constituent of alloy may be there in the powder. We don't know. Put together only it will become an alloy again. The alloy segregation should not come. The uniformity of the component is very important for ISRO actually. That is one important challenge which we are posing for all people who are working in 3D printing area. If you really want to contribute to space segment. PS4 tanks through additive manufacturing. Actually, direct energy depositor method is one method what we are really going to follow. And powder development for future. So these many powders are to be developed minimum if you want to make columbium C103, copper alloy, CU nickel alloy actually, C273 titanium alloy BT5, TI6L4V, TA 2.5 and 2. That also half alloy, also alpha beta alloy also you have to make. Nickel alloys. These are all Russian alloys actually. Stainless steel, 321, 304, 316L. Everything we have to make right now. Space quality. That all. Space quality, you must understand what all these things are not commercial quality. Space quality means the oxygen content will be less, the gas content will be less, the porosity will be less. All will be very strict. The AMS standard what we are following for space totally 1 order higher than the commercial products. Spacecraft component subsystems what we are following in SAC Ahmedabad, Satellite Application Center Ahmedabad. Some of the components what we are 3D printing, I'm just sharing with you here. So materials like 6061 BF2 SWP to 2024 copper magnesium alloys like 1B H24 6L4V 300-400 series of steel, beryllium copper alloy, non-ferrous like FRP, fiber reinforced plastic, PTF, and Derlin and nylon, etc. All can be 3D printed. This center, you must understand 90-95% is material is removed right now through CNC or wire radium method. Right now, the way in which you produce, and there's a lot of waste of material happening. To produce 10 grams of small components, we'll be wasting around at least 300 grams of forging to see that it is being made. The scrap cannot be used for anything else. It is a waste actually. The machines have to be 3-axis, 5-axis, and it's going to be highly costly. So if you go for 3D printing, we can save a lot of material that need to be cataloged and counted so that then only we can prove it more economical. Dimensional accuracies are generally 5. You must understand even forged parts or even formed parts like sheet metal parts also we require for 5 microns, 50 micron accuracy. Very difficult to get sheet metal accuracy for 5 microns, 10 microns. We are looking for that. And surface finish is 0.5 to 3.2 microns. This is another challenge which we are really posing for 3D printing. So 3D printing doesn't avoid the 3 CNC machining part. If you go to near net shape, after that again you need to go for CNC machining to get this kind of finishes. So that is another challenge we are going to have. It's not really going to do away with my 3 CNC machining or anything machining. That machine still need to be there to see that the entire product is finally finished to the actual component, actual shape, from the near net shape to actual shape. So avoiding CNC machining in the final phase, if it is possible in 3D printing, and if you're able to get an accurate product by 3D printing alone, that is going to be really a kind of a boost for me. Otherwise, no, the 3D printing machine I'm not able to avoid. So these are the things which you really look into when you really want to create. Final machining is still there. So these are typical parts by Satellite Application Center Ahmedabad. They have gone into brackets and all. Some of them they already made in Tron also by 3D printing. You can see this. The parts that we are shown in rocket engine components are totally different from the total structure as well as the even configuration. Everything is different for the satellites. You see, these are satellite structural parts. Honeycomb panel assembly. They are typical parts. You can see here additive manufacturing from the component rapid manufacturing and rapid prototyping from concept modeling. It has evolved into additive manufacturing right now as a technology. This is not a new technology. Sometime back, no, Boolean algebra. If you want to construct this solid geometry, if you are making through from circles and other things, no, if you want to make it, it's a kind of additive, and the other one is subtractive. What we are really doing is subtractive actually. So the reference taken are totally different in machine also. You must understand that. So the entire thing is totally a different product. Even design concepts are different in your FEM analysis, everything. Concept prototype using your fused direct. 1 minute. It's okay, fine. Okay. Yeah, fused direct metal technology actually. This is fused direct metal technology. We are producing some components. These are also satellite components actually. And future functional prototypes right now. You can see this. They're all again 3D printing functional prototypes by some other mechanism, then finally migrate to my actual metal. What we really here you're proving the configuration first, and then going for actual product. Elliptical tool. for CFRP components actually is a SPF mounting plates for electronic components mounting these plates actually. This also can be 3D printed. Otherwise, you have to go for a big machine and machine it out. 3D printing is but only thing here also big machining is required. You can't, otherwise no, the size of the machine is not going to come down here also. But you require a typical tailor-made 3D printing machine for this also. Aim for insulation of ultra-light thermoelectric elastic material actually 9085. Here also we are using 3D printing actually. Some other non-metallic material also. Validation of ULTM has been completed by 3D printing already in SAC. Proposed payload is 17 parts consolidated to 2 parts actually here. This is the advantage we are going to get. This is designed for AM. Housing down link coupler, 3 parts consolidated to 1. Space payloads, communication payloads, navigation payload, remote sensing payload. 3 types of payloads are there for 3 types of applications. Micro remote viewing payloads, all these things here. Here also we are finding some application of 3D printing. See, design approach for this is fabrication. You can see the kind of mechanical design and fabrication in short time with minimum weight, design intricacy, compact, simple configuration, stiffness, strength, design for manufacturing, ease of fabrication, thermal management. For all these things, we need to see the other, whatever other factors which doesn't come in the other component manufacturer. These are the other parameters and other ethics coming in the space component manufacturing and fabrication. Accessibility, tools, and torque. So torque, it means accessibility should be there. Otherwise, no, that also another design factor coming into picture. So in the rocket, the accessibility is very less when you put along with other components. So torquing accessibility should be there. All these things should be foreseen and the component should be made. Otherwise, no, you'll be ending up in trouble when you really want to integrate the component. Communication payloads, you can see that all these things are 3D printed. Material invar, magnesium, titanium, and composites also are coming into picture. Tight geometric and diameter orders are required. Low alpha materials. Aluminium alloy machining through DMLS. Aluminium silver powder actually. This is an importer powder actually. You know, on one company which we are making this, Indomim is the one company which in Bangalore which are making some of the alloys for us actually. One alloy company which some of the alloy for us for 3D printing. For the prototype so far, they had to go for a commercial scaling up. DMLS printed parts, typical, cluster down to space, 10 lakhs. This is run by Wipro. It's already flown actually. With cluster flown, already flown in the last our GSAT satellite. GS19 feed structure. This also already assembled and printed to single part actually. Aluminium, magnesium, silicon, magnesium alloy. So the expectation from industries, surface finish of the order of 4 to 5 microns or better are required. Diameter accuracy of the order of plus minus 20 micron or better. And redesign the topography of hardware to suit 3D printing. Machine for realization of hardware sizes larger than 400 mm. Cost-effective approach. Industry should also take up work for post-processing machining and surface treatment of electroplating also. We require anodizing, electroplating also. So all these also, the entire end-to-end production need to be taken up in the industry. We can't go for piecemeal this one. So in conclusion, learnings what we have taken from the 1-day 3D summit and our experience so far in 3D printing for space components, opportunities do exist in select areas. Replacing the operational space system with 3D printed components, not always optimal. Parameters of cost, reliability, efficiency, etc. have to be seen one by one, case to case. Adoption of design to print, design to additive manufacturing philosophy for next generation space system, what we are going to follow. Evolve qualification procedure for 3D printed components. So that's what I told some time back, how to qualify the components when you make 100 numbers from different. The process qualification is very important for us, not product qualification. If you make 100 components from one forged block, my qualification is very easy. One block qualification is easy enough for me to qualify 100 components. So that is going to be a different system approach here actually. And powders and atomizers, all these are alloys. A few of them I have mentioned here. Many more are there actually, are to be made in India, and atomizers are to be available. Completely indigenous supply chain for 3D printing domain to avoid pitfall of imports, to make it Atmanirbhar. Okay. So that is one challenge we are posing to all industries or all research scholars or all people who are working on this area right now. And thank you for your patient listening. I feel I have conveyed exactly through some of the slides here, a cross-section of slides here, a kind of flavor of what exactly is going on in 3D printing area in ISRO, as well as what we are looking for, and what are the small bottlenecks what we are facing to migrate to 3D printing at a faster pace. Thank you so much.
Thank you, sir. Wonderful insights on what ISRO is doing in 3D printing and what are the challenges you face in space applications. And you also told that whenever there is new technology comes, there will be a lot of hype. But we should understand, realize its potential and how to migrate from conventional to the new technology. Adopting it is a very challenging task. It's not that it can happen overnight, but it can happen only with proper understanding of the technology and what are its limitations. And it's a very, I think this FDP program got today a clear picture what is 3D printing and what is the future of it, what are the challenges. Now we are given lot of research areas where because this is mainly to academic faculty members and startup companies and other people are very much into 3D printing participating. Around 200 people from across India are participating in this are online. And I hope your lecture, your keynote lecture given an insight what we have to do in future, what are the research areas we have to work. As you have said in your open hand that ISRO is ready to accept the ideas from any people, what are the challenges you have thrown. If you come out with proper solutions, ISRO is going to support that. And I hope it has given a lot of insights to all our participants. Now the session is open for question and answer. Any participants, you can post your question in the chat box, or I will switch on if you raise your hand, I'll make you one of the panelists. You can switch on your video and interact with our esteemed speaker, please. Any questions? Sir, one question is coming, sir. I think, okay. Okay. Basically, the one question is, sir, what are the constraints I have to take in? I think he is asking the challenges in the material properties that you look when you go for space applications.
See, it depends upon the end use actually. If it is a cryogenic engine, inner chamber isolate, we won't look for thermal diffusivity, like physical characteristics like thermal conductivity, so many things. Like thermal expansion coefficient should be linear, it should not be non-uniform, should be uniform. The expansion, we should be able to predict even all these things. So physical constant as well as mechanical properties like UTS, YS, and hardness and modulus of rigidity. And all these things are important for us actually, and the uniformity across the entire thing, that is more important for us actually. So in 3D printing, what exactly people are suspecting is that uniformity can be proven only through a PPT, proof pressure test. If you really want to test one coupon and validate, is not going to be possible because each and another thing what we are really going to challenge, what we are going to face is aluminum alloy. If you want to 3D print, it should not get oxidized. It should be in inert atmosphere actually. So it should be in inert atmosphere, then only it can be 3D printed. If it is getting oxidized, again to become inferior quality. So that is another important thing, that you need to have an inert atmosphere to see 3D printing. There should be vacuum or inert or in helium or in argon atmosphere. So these are important challenges what we are facing. Otherwise, the component manufacturing and if you want to really make a hemisphere or a cylindrical or a propellant tank, the final qualification for me is only proof pressure test finally. Going for 1.2 times your mean operating pressure. That is going to be, otherwise, I cannot prove my material uniformity to my design people unless I do it. So the component has to be finally made, then only you can test. I am not going to testing the actual material and going to make the component, which is finally after the entire thing is made, and if I am forced to reject it, you know how much of a cost and effort is going to be wasted. So a priori testing and a test coupon and thing is not possible the way in which we are doing right now in all mechanical components is not possible in 3D printing, because for me 3D printing, each of these small micron molecules are different and they are only integrated, fused together. The uniformity I can test only when it is being completely tested as an integrated product. You are not audible. No, you are not audible. Yeah, now it's okay. Fine. Yeah.
Right. After printing the part, how do you qualify the part for testing in real environment?
That's what some time back I told. No, you have to put it in the engine and do a hot test, and to really do a hot test in the test stand in Mahendragiri. In ISRO Propulsion Complex, IPRC Mahendragiri, you have to do a real, and that hot test is going to cost me nothing less than 70 to 80 lakhs. So I cannot go for a single component alone. For single component testing, the value of my component, more than 3D printing, the value of testing will add up to my component cost, and I will not be able to make it economically viable. No. So unless I do a hot test, I can't see. Even through the conventional method, what I'm following, I have to do a hot test before flying. That is the ultimate test for me. So if you want to really do a component with 3D printing also to be qualified, you need to undergo a hot test. So one of the way of doing thing is the next engine, whatever is going to really fly, there is the hot test is inevitable. But I can go for some 3D printed replacement parts in that and test it so that it can fly. But the problem is, who is going to allow me for for testing in the test stand with a different component? Because if anything happens there in the test stand through a different method, what you are following, some anomaly or some kind of accident happens, the entire test stand will be blown off. And the test stand is only unique one available for me. So who is going to allow me for going for this test if I replace with another part? Who is going to give me the confidence? If I ask somebody, the review forum should allow me to go for a test.
Yes, sir.
So the test stand is blown off means I cannot test it for future for some time, and it is going to be a handicap for me. And the test stand is crores of worth investment actually. The capital investment is too much for close test stand. So the first, you can ask me the first test, how did you do? We are taking a risk. Definitely. But somebody need to give confidence to me that this component what I replace with 3D printing will behave exactly similar to what we have been doing through other method or superior to that. By not by physically and on numbers and paper I have to give, then only the review forum will allow me to go for this particular hot test. After the hot test only it's qualified.
Hot test.
Hot test means real firing.
Okay, right, sir. That's all. So, still anyone wants to interact with sir? And post your question, that I'll, if you can unmute yourself and ask, you can raise your hand also. Mr. Venkatesh, you want to ask 3DP013? Hello? Sir, one person is asking, Abdul Junaid, which is the better material in 3D printing which can replace jet plates without compromising application features?
Right now, we are all using Inconel and Inconel 718 material for 3D. I think same material we can use for 3D printing also.
Yeah.
So, but only thing is the powder has to be made uniform.
Correct. To avoid porosity and other factors.
Yeah.
Made uniform. Defects to avoid. Okay. Still, anyone wants to have questions related to space application, because there is a lot of potential, as sir was telling, there is a lot of potential and lot of areas, gray areas where you can do a lot of research and improve from the existing, migrating from a conventional 3D printing. So I hope this will be a very good, anyone is pursuing his PhD work, etc. These are the areas where you have to work, especially the space and the biomedical applications. I think we had a sessions on biomedical also. So one question from
biomedical is catching up like anything.
Anything, sir. Actually, we had two doctors presented day before yesterday on orthopedic application.
Knee joint, knuckle joint, your wrist joint, all biocompatible titanium, no, all these products, including heart walls.
Correct, sir.
Heart walls also made of now titanium 3D printer parts.
In fact, we had two sessions, sir. One is Dr. M.V. Reddy, who has done 25,000 hip replacements. He was using 3D printing for using, he has his own printer in his home, sir, 4 printers. He is using it. And I hope you heard about Professor Guruvareddy Garu, Sunshine Hospitals. He is the person along with him. And we also had a session on what you call from Dr. Abhinandan, he was working on bachelor fit
after the radiotherapy, the jawbone has to be replaced. The jawbone.
Yes, sir.
Jawbone configuration of each person is totally different from another person. So it has to be customized. So
Yeah,
customized product, even hip or even this jawbone customized products can be easily 3D printed as per your real jaw configuration or real hip configuration. So that is going to be really advantage because it's only unique one of product for the particular person.
Correct, sir.
For such unique one of products, the 3D printing is very, 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 very.
We have to shift from mass production to mass customization when it is required. And
depends on which
depending which way you are working.
Not the answer universally for everything.
It's not universal.
It's a good technology, but it has to be adapted very selectively.
Correct. Sir, we are joined by our principal, Professor M. Kumar, sir. Sir, I invite you, sir, Kumar, sir, for the valedictory function. So, some more questions, sir. Meanwhile, sir is joining. Sir, this question is, I'll now try. I came across some topics, sir, very informative presentation. You spoke about what potential 3D printer has now. Thank you. I came across some topics like 3D printing food and medicine in space. What is your opinion on that, sir?
3D printing is actually, additive manufacturing can be used for anything actually. Even pharmaceuticals you can use to make this one. There is NASA is working on a technology which on Mars, if you want to really have like igloo. Igloo has been, you have seen igloos, no, in Himalayas and all, like hut being made. So such hut, if you really want to make for habitation in Mars and all with materials, concrete and other things.
Yes.
Control from here, ground, giving commands from here. 3D printing is going to be the best technology for making such huts in Mars in the years to come. Correct. So for what, if you want to go and stay there in the initial stages of your colonization, after going there and staying there, you can make another house. That's another thing. But if you really go there, if you want to go for the initial stages, you must be having some place to stay. So that all they are envisaging 3D printed igloos and huts for them to stay. Unique model. So this 3D printing without gravitational force.
Yeah.
In space while flying.
Yeah.
That is another thing, because each powder you must understand one thing. Alloy making and without gravitational force is one of the important areas of research what is going on right now, because alloy segregation will not be there at all. Alloy segregation is one important. Alloy component segregation is one important thing. Constituent segregation is one important problem what we are facing right now. When you really want to go with light and hard alloys mixing together and making an alloy, homogeneous alloy, it will always, even though it looks to be seemingly homogeneous, is always heterogeneous actually.
Yes.
Not be having uniform properties. So in space, if you want to go, the gravity effect will not be there. You can have a uniform, really uniform, what you can call isotropic. The real isotropic properties, you can, whatever we call here at Earth in isotropic is near isotropic. The actual isotropic products you can make only in space. Once you go for isotropic products, its uniform properties all through all directions, then you need not even test. No PPT, nothing is required. A lot of cost can be saved. Once you can prove, once you can 100%, you can be sure that isotropic components are materials are being made. You can go for, without testing, you can go for flying. So that is one area where without gravity effect, it can only be done in and as a manufacturing process, 3D printing is one area, because you cannot carry various machines like milling machine, drilling machine, all these machines too, because inert mass carrying to space is going to be really cumbersome, and you have to pay a lot. The payload will be too much. So one single point solution for all drilling, milling, everything is only 3D printing. If you really want to, you look into all processes being replaced by 3D printing. So carrying one simple 3D printing machine, you can do a lot of things there. So because of that 3D printing, because of that particular advantage of carrying only one machine in place of 100 machines or N machines, 3D printing acquires maximum importance in space manufacturing because of a unique feature. So, but under gravity manufacturing, under no gravity, zero gravity, and vacuum manufacturing, in vacuum also, your 3D printing is totally different from what you're doing in Earth here right now with gravitational effort. That need to be again research and to be again optimized. Not audible?
It seems NASA has sent one 3D printer to International Space Station. We have seen some.
Yeah, right now, 2 weeks
right
back.
now.
2 weeks
2
back.
weeks. Yeah.
To repair something there.
Correct. So it is like we call move the expertise without moving the expert. That's what we put there.
Can be controlled from here. That is the advantage. Can be controlled from here. Don't need another machine is going there.
Yeah, our expertise is moved from Earth to space through this connectivity. I think you have obtained. Sir, I think there are any Mahipal, someone is asking, switch on the video, you have to interact. Anything to say? We'll wind it off this session. So, sir, anyone still? 3D printer, okay, right. Okay, sir.
Okay.
I hope we'll stop. Sir, thank you very much on behalf of the organizing committee of this 3D. We are joined by Professor M. Kumar, sir, principal of our college, sir. Kumar, sir, you are welcome, sir.
Good evening, sir.
Kumar, sir, you can switch on your videos. Professor Kumar, sir, our principal and also executive committee member of our Usman University, sir. He joined for our session, sir. Sir, Dr. Venkati Krishnan is on the line, sir. Sir is delivered just now a very innovative talk on application of 3D printing in space, opportunities and challenges. He has shown a lot of areas where you can do research for all the participants. I think I should thank sir because I think I don't know sir at all, but through my known friend ISRO Shankaran, and I think I got contact from sir. And when I called him, he was so generous that he has spent nearly half an hour time, sir, to spend me about talking about what are the inputs you require, everything. So I think we was very thankful to him for coming across in spite of a busy schedule and to be the keynote speaker at the end of this session. And then we had this sir is going to the chief guest for valedictory functions. So sir, you can meanwhile start. I will talk with the Venkatesh. Safe.
Good evening, Professor Kumar. I think you're on unmute, sir. You're unmute.
I'm unmuting. Sir, I'm unmuting, sir.
Yeah.
Kumar, sir.
Yeah, is it audible?
Audible, sir.
Now it's audible. Yeah.
Sir, Professor Kumar, audible.
Thank you for your valuable time, sir. Thanks for spending your valuable time and accepting our invitation and delivering a great lecture. Audience, definitely they might have benefited a lot because I not listened your lecture because I am on some other meeting from 3 o'clock to 4 o'clock. Definitely, it's a great kind of help to the faculty members, those who are attending this particular program. Shivaramakrishna ji, shall we start the this valedictory session now, or time is there?
We can start, I believe, because
Hello?
4 to 5 he told, no?
Yeah, 4 to 5. That's what. No problem, sir. No problem, because we have time. Yeah, Dr. Shivaramakrishna is a excellent, person. Is nicely organizing the programs, series of programs, not one, right? And he always works with a keen interest for the benefit of the institution in particular, and for the sake of faculty members across the country.
I think Shiva has to unmute. Shiva is not audible.
Sir,
Yeah.
sir.
Yeah.
Sir, Venkatesh is in his examination ran some power failure. He is joining from our college, sir. Joining within 1 or 2 minutes. We'll start.
Okay, he's coming now?
He's coming, sir. He's coming. It seems Ramesh Babu, sir, has got some problem through the power failure, so he's unable to join, sir. So we'll continue
Okay.
our program, sir. We'll
Yeah,
continue.
no problem. What about registrar, sir?
Registrar, sir, I asked Venkatesh, sir. He's in touch.
Okay, fine. Yeah.
Once
Once
Venkatesh
Professor
joins,
Sriram